So lenses, yeah, most of us wear glasses. So we know lenses are important. Cameras, the expensive ones, the expensive part is not the shutter, not anything else except the lens. Because chiefly a lens, if improperly made, can have at least 7 types of defects. 7 types of defects. And we'll talk about 2 of those defects. And when a lens is made with no defects, it's going to become expensive. That's why cameras are very expensive. It's because of the lens. Because we want the real colors, right? Do we want a white object to look colored? No. Now that is a defect. That is called chromatic aberration. Chrome itself means color. The word aberration means mistake. So chromatic aberration, defect in color. So what is chromatic aberration? A white object, when you take a picture of a white object, it'll appear to be colored, like rings of color. Why? I didn't intend to start this way, but I did. So this is because the refractive index of violet is greater than the refractive index of red. Each wavelength has its own refractive index. And you know white light is made up of all the 7 colors, right? Come on. So when white light passes through any material, each color is going to bend a little bit different. Which one is going to bend more? Violet is going to bend more. So the focus would be at different points, wouldn't it be? Violet would focus closer and red would focus further away. So that gives you, if all the colors are not together, you don't get that white again. You get it all dispersed. That is called dispersion. What is dispersion? Dispersion is the separation of colors. Dispersion is the separation of colors. And why does it happen? Because each color has a different refractive index. Okay, we'll talk about that and we'll see how it's corrected. So lenses are important. And these are the types of lenses that you have basically. I'll run through those. Biconvex lenses. Bi means both sides are convex. Plano convex. One side is plane, the other is convex. These are the contact lenses. That's why they're called meniscus lenses. Meniscus means surface, so they're like thin. See? That's why these are the 2 types of contact lenses. And then you have the plano concave, one side plane, the other concave, and then you have the biconcave. Usually people talk about these 2 lenses. Those are the only 2 people know. Both sides convex, both sides concave. See? But I'm trying to tell you that one side could be plane, the other side could be either convex or concave. So those are the types of lenses that you have. All right. When light passes through a convex lens, so that's a biconvex lens, and you can see that the rays are parallel. The incident rays are, aren't they? They will all come to focus. After refraction, they all come to focus. And technically there will be 2 refractions, right? Watch this. Wouldn't there be 2 bending, one here and other here? One when light goes from air into glass and the other from glass into air. Come on. But we always assume that the bending takes place in one step right in the middle. See, when we draw diagrams to make it easier. But you just need to know there's always 2 at the 2 surfaces. Now, convex lens is called a converging lens. Why? Because it really converges. But a concave lens, look at the difference. Look at the concave lens. Parallel rays are bending away. So do you think that these rays will meet each other? No, they won't. That means you'll have to imagine that they come from one point, isn't it? And once you imagine, I've told you that point is not real, it is virtual. So, which lens has a virtual focus? A concave lens has a virtual focus, which is exactly opposite to what we had in the mirrors. In the mirror, a concave mirror had a real focus, and a convex mirror had a virtual focus, okay? But for a lens, it's the opposite. A convex lens has real focus, and a concave lens has virtual focus. Don't you think that's important to know? Why? Because if the focal length is virtual, you got to take it as negative. So you have to read the problem carefully. If the problem is talking about a lens, you first have to make sure if it's a mirror or a lens, please. If it's a lens and if it's concave, you will take F as negative. But if it's a mirror and it's convex, you will take F as negative. I told you, that's the only thing you have to be careful about. The power of a lens is the reciprocal of its focal length. The power of a lens is the reciprocal of its focal length, but be extra careful. The focal length has to be in meters. Now, this is the one thing I was talking about. The power of a lens is the reciprocal of its focal length taken in meters. All right, go ahead, find the power of a concave lens of focal length 20 centimeter. Find the power of a concave lens of focal length 20 centimeter. Be careful. Is that clear enough? The power is going to be -5 diopter. Okay. What lens is that? Convex. Both sides? Biconvex, correct. And that's the object. And actually, to find the image of this point, you only need 2 rays, but I have drawn 3. Because if you draw any number, it'll all meet at the same point, you see? I just wanted to show that. These are the rules. If you draw a ray parallel to the axis, you see the axis? If you draw a ray parallel to the axis, it has to go through the focus. And a lens has a focus on either side because it's transparent. It'll have a focus on both sides. And if the 2 surfaces are equally curved, then the focus will be at the same distance. Okay? So a parallel ray goes through the focus. Look at the second ray. It's going right through the center of the lens, isn't it? That point is called the optic center. If a ray goes through the optic center, it will not bend. That is the only point through which, when a ray passes, it does not bend. And you know why? Because the angle of incidence is 0 degrees. That's why. No bending. If it's along the perpendicular, there is no bending. So it does not bend. So that's the second ray. What about the third ray? Did you notice how it is going? It's the opposite. Correct. If it passes through the focal point, it has to become parallel. Exact opposite of ray number 1. So do you see that all the 3 actually meet here? So what kind of image do you get? Is it real or virtual? Real image, because they actually meet. Are you with me? So, and is this going to be an upright or an inverted image? That's the head of the image. Because it started from the head of the object, that's going to be the head of the image. So that is going to be inverted. It's a real image. Remember, there are 4 properties for any image. Let's get the 4. It's real. It's inverted. It's beyond the focus. Isn't it beyond the focus? And isn't it slightly magnified? I think when I complete the diagram, it's magnified. Okay, so that's the optic center. That is the image right now. And whenever you draw ray diagrams, please do not forget to put the arrows. If you forget to put the arrows there, you lose a lot of credit. You have to show what direction it's going in. It can't be lines. It has to be rays, right? Okay, so that is how you get that image. It's real, it's inverted, magnified, and it's actually beyond twice the focal length. Why did I say twice the focal length? Because you see, if that is the focal length, twice the focal length would be somewhere here, isn't it? Which would be the radius, remember? Because radius is twice the focal length. And this is gone even beyond 2 times the focal length, okay. What happens if I move the object closer? Can somebody draw a diagram? Not somebody, everybody. Try to put the object here, inside the focal point, get the image for me. I'll give you 3 minutes. Parallel, what happens? It goes through the focal point. So draw through the focal point. And then you only need 2. So if you draw the second one through the optics, I missed it slightly. So if you draw it through the optic center, that's better. You see that it has to go without bending. And now you see that they're not going to meet. Do you see that the 2 rays are not going to meet? Aren't they separating further away? And I may not get it on the screen. I can move this. Because I need to extend it backwards now to get the image. Correct? Yeah, I can't get the image. There's no real image. Because these 2 don't meet. So let me move this whole diagram to the right side so I have space on the left. And then you will know what I'm trying to say. Okay. So now what I have to do is, to get the image, I have to extend this backwards. I hope somebody gets what I'm saying. Straight backwards, and I should not... Yeah, I should not bend it there. It should go straight back. And no, it's almost parallel, so it's going to meet somewhere there. You know what I'm trying to say? Because it...
Beyond the wall.
Somewhere there. But what's important is, what kind of image is this? Is this real or virtual? Virtual. Do you see that it's an upright image? Only virtual images are upright. That's another point you have to note down. If an image is upright, it's virtual. Whether it's a mirror or a lens. Somebody put their hands up? Yeah. Oh, okay. For a mirror or a lens, if the image is upright, it is virtual. Which means if it's inverted, it is real. So you get so many pointers, you see, and you have to have all this information and try to answer the questions. It's important to keep it connected to reality. What is the lens that we have in our eye? Is it? Pupil is the opening of the eye. You know. Is it convex or concave? The eye lens. It is convex. It is convex. And what kind of image does it produce? Don't say it if you don't know. It produces a real image on the retina. Because a real image, only a real image can be produced on a screen. See, because the virtual image is like imagination, isn't it? Mm-hmm. So since we need to get an image on the retina, it is the screen. See, the retina is the screen. And what is produced is a real image. Are you getting me? Which also means that it's inverted. Didn't I say that all real images are inverted? And it's our brain that turns it around. All the images that we get on our retina are inverted, yeah. All the time, everything that we see. In fact, there was an experiment that was done some years back where they had special kinds of lenses made that would make the person, as soon as the person puts it on, he would see everything inverted, right? And this person, you read about it? This person had to wear this as long as he was seeing, except at night. And after a few days, he started seeing everything upright again with the lenses. Because our brain self-adjusts. And then when you remove the lenses, everything went back to inverted. He had to go a few more days. I want to tell you something, and you may not like this, but our brain gets used to what we feed it. Our brain can accommodate. So if there is a certain thinking that we give our brain day in and day out, it just gets used to that. It says, yeah.
Same with the bike. There's a bike where instead of when you turn right, it turns the other way.
Right. Before you draw, what do you know about a concave lens? What do you know about a concave lens? Its focal length is negative, which means it can only produce virtual image no matter where the object is. You can have it close, you can have it far away, wherever. It can only produce a virtual effect. There it is, right before your eyes. But that diagram is missing something. Can somebody tell me what it's missing? The arrows. No, the direction. Hopefully I put it later on. Oh no, the arrows are there at the ends. Yeah, I didn't see that first. At the ends, yeah. So that is the image formed by a concave lens. A concave lens is a diverging lens. A convex lens was a converging lens. See that? This is diverging. Did you notice that the image is smaller? Concave lens. Or which lens would you use as a magnifying glass? Convex, because this image is going to be smaller. Look at that. Isn't the image smaller? So how would you use a concave lens to magnify if the image is going to be smaller? So the magnifying glass is a convex lens. So what is a telescope made of? Convex lens. What are microscopes made of? Convex lens. Because in all those cases, we're looking for magnification. In fact, we use multiple lenses there. At least we have the eyepiece and the objective. You know what that is, right? 2 lenses. In a microscope, don't we look through one lens? That's the eyepiece. And there is another lens at the end of that long tube, which is kept close to the object. That's called the objective. Do you hear me? Microscopes and telescopes have 2 sets of lenses. The fact is that actually these lenses are also combination lenses. They're not single lenses. So I can't even say that it's 2 lenses. I have to say it's 2 combination lenses. You understood? Kept at the ends of a tube. Why do you put it at the ends of a tube? Because you should be able to adjust the distance between the lenses. You know, when you turn that knob around, what are you doing? One is the eyepiece, the other is the objective, and you're actually changing the distance between the 2 lenses. When you change the distance between the 2 lenses, you're changing the focus. Okay? We'll go into that in a bit. But have you understood the diagram? What are the properties of this image? Is this understandable? It's virtual, it's upright, it's diminished, and the image is always going to be between the optic center and the focal point. The image is always going to be trapped between those 2. Now what I did here is I put all the 3 images together so you can see the difference. Now that is convex lens or converging lens forming a real image. And you see where the object is? It's beyond the focal point. Do you see that? But if you bring the object close, see that the object is now inside the focal point? The same lens produces a virtual image. See? Those 2 are for a convex lens. Now for a concave lens or a diverging lens, wherever you keep the object, you're going to always get a virtual image. This is what we just looked at. So I wanted all the 3 to be together. You can make that difference out. Are you able to make that?
So let's say we put an object there. So that means that
Human eye and corrective lenses. Human eye and corrective lenses. I can tell you without any doubt that there is no camera that's ever going to be made that is even 1% complicated as our eye. The eye is such a complicated organ. We can't even come 1% close to that when we try to make a camera. I'll give you some of the complications that it has. One is the accommodation of the eye. Like I'm reading, I can see it clear. I look at the stars, it's immediately in focus. You don't even feel the difference. You know, you read and you look at an object far away, immediate focus. You can never have that in any camera. Second is the depth of vision. You've all noticed that in movies and all that, when they have a camera, they have to focus on, if like there are two people, the camera can only focus on one person and the other person will be shown in the background. You know what I mean? But look at the eye. You're all at different distances and I can see all of you clear. Amazing. It's all clear. Immediately I take a book and read, it's clear, and I can see the print and all of you, whatever distance. And what is the range of the human eye? Up to infinity. The eye can see up to infinity. Proof? How far do you think the stars are? They are billions of light years away. You know that, don't you? But we still see them. So the range of the human eye is infinity. The accommodation is infinite. You know, but what's important here is the eye has a lot of parts and all that you do in biology. But what's important is 2/3 of the refraction takes place in the cornea. 2/3 of the refraction when light passes through the cornea, it bends more than it bends when it passes through the lens. Did you know that? Only 1/3 of bending takes place in the lens and 2/3. So that means the 2/3 of bending is fixed. And the 1/3 is flexible. What do I mean by flexible? When you look at an object that's very close, the eye lens becomes thick. Because of the ciliary muscles, you know, it'll become thick. That means its focal length becomes small. When you look at the stars or anything farther away, the eye lens becomes thin. Are you getting what I'm trying to say? So the focal length of the lens adjusts, while the cornea is always doing the same thing. It's just bending the same amount. The purpose of change in focal length of the lens is to get the image on the retina. All the time, you got to get the image here, right? And you all know that we have a blind spot, the optic nerve where it connects to the eye. Did you know that? Okay, if you move an object close to your eye, there is a point at which you won't see it. Don't try it now. Because if the image forms exactly here, there is no retina there. You know, it's the connection of the optic nerve. In the eye, you have what's called rods and cones. Rods enable you to see dark and bright, and cones enable you to see color, blah, blah, blah. So all that is there, but there is a blind spot. Okay. Well, what's important for us to know the defects of the eye and how to correct them. That's what you do in the physics class, but I just have to talk a little bit about this. Here are the refractive indices. The cornea is 1.376. The lens can change its refractive index from 1.386 to 1.406. And I'll let you write that. The eye. The near point of the eye is the minimum distance at which you can read something. I'm talking about a normal eye. What do you think is the near point of an eye? Normal eye. For an adult. You know why I'm saying this? For little children, and moms do not know this, so for little children, the near point is really small. If you watch little children, they will hold the book very close to their eye. Have you noticed that? Because they can see even up to 10 centimeters or 15 centimeters. Moms, dads don't know this, so they'll say, hey, put it away. No, as they grow, their near point shifts further and further. When you become an adult, it's about 25 to 30 centimeters. That's why they hold the books so close. They can see clearly.
Makes a lot of sense.
Because we can't, you know. We can, so we will. I've seen that 100 times, and it's tough to explain it. So
I see it every day with my little brother.
there you go. But in a problem, if you're given the near point, you got to take it as 25 centimeter. The near point of the eye, you will have to take it if nothing is mentioned. If it is mentioned that it is 30 centimeter, please take 30. You know what I mean? If nothing is mentioned, by default, you're going to take it as 25 centimeter. Okay, what's the far point? I already mentioned that the far point is Infinity. You can see everything. So the human eye can see everything between 25 centimeter and infinity.
Can't focus that far.
For the normal eye, we can focus that far. Yes, we can.
No, I mean, like, it can't magnify what's.
Yeah, the size will appear to be different, but we can see that clearly. All right, let's move on. The first defect is nearsightedness. Nearsightedness is also called short-sightedness or myopia. Myopia. That happens because the retina gets elongated along the x-axis. The retina is elongated along the x-axis. Watch. It just got an oval shape like that along the x. So if it had the spherical shape, the retina would have been here. Are you watching? See? The retina would have been here. Isn't that where it's coming to focus? But now because of the elongated shape, the retina is here. So for this person, nothing will be clear because the eyeball has changed its shape. It's got elongated along the x-axis. So that's the problem with nearsightedness. How do we correct that? It's very clear here. You correct it by using a concave lens. Why? Because a concave lens is a diverging lens, isn't it? Because it's a diverging lens, it's able to push the focus further away. See, it's able to diverge it away. You want it to be, you want the image to be on the retina, don't you?
Mm.
What would happen if you use a convex lens? It would push it further in front. You see that? So short-sightedness is corrected using a concave lens. So that's how it's corrected, by using a concave lens. We have to work out problems on this. And the far point now, unfortunately, is not infinity. See, you can't get everything. Nearsightedness. Wait, let's get this very important point clearly. For a normal eye, where is the far point? Infinity. If somebody has short-sightedness, this would be the most important point I'm going to say today because it goes straight into doing problems. For somebody who has nearsightedness or short-sightedness, the near point is not changed. The near point is still 25 centimeters. What changed was the far point. This person cannot see objects up until infinity. But surely the person can see, let's say, up to 20 meters. Instead of up to infinity, the person is able to see up to 20 meters. Are you listening? So how do you correct it? You have to put a lens, a concave lens, which would produce an image of an object which is at infinity at 20 meters. I'll try to say that one more time. And this is a very confusing point for students because they don't listen, that's why. This guy cannot see up to infinity, but for example, he can see up to 20 meters. Okay, I'm just saying 20 meters. So how do you correct his vision? Put a concave lens. What should the concave lens do? The object at infinity, the concave lens should produce an image at 20 meters from him. Because after that, his eye lens will take it on. Because he can see anything up to, are you with me now? So the concave lens, last time the concave lens should be able to produce an image of an object, DO infinity, DI should be 20 meters. Now again, because it's a concave lens, DI is going to be negative. Because a concave lens can only produce a virtual image. So what should be the power of his lens? Go ahead and calculate. I already did a problem there. Go ahead and calculate. DI is infinity, DI is negative 20 because he can only see up to 20 meters. What's the power of the lens he must wear? Okay, 1 by infinity is 0, so that's gone. Which means 1 by DI is 1 by F, which means DI is F. So the focal length of that person's lens, corrective lenses, must be negative 20 meters. Isn't that what I'm saying? So what's the power? Power is 1 by F. So it should be 1 by negative 20, which is
Negative 5.
Which is a real small power. This guy can easily live without corrective lenses because he can see up to 20 meters. See that? But what if a person can see only up to 5 meters? Go ahead and find his power. 5 meters. The far point is not infinity, but it is x meters. X was 20, right? Was 5, could be anything. The far point is not infinity, but it's x meters. And so the lens produces image at x meters of an object at infinity. If you know that, you can do any problem. It's called hypermetropia or hyperopia. And it can be many reasons, but it could also be due to the shape of the eye getting elongated along the y-axis. So the other one was, so it's basically losing shape. You know, the spherical shape is lost. So this one gets elongated along the y-axis. I mean, that's not very clear there, but it's very clear when you look at where the image is. Where is the image? Here? You know why? Because this got like closer and got elongated here. That's why. So you want to push the image forward. What kind of lens would you use? You want a converging lens, right? What's the converging lens? Everybody can say con, but what comes next is the con. Yeah. Convex. Rudy is trying concave X. I heard him. Okay. So convex lens. So if you correct it using a convex lens, then you get it back on the retina, which I've drawn now. So I made some modifications. So if you put a convex lens here, you're going to get the image back onto the retina. If you don't have this lens, then it's going to be here. See? Okay. Corrected using convex lens. Now here is where you have to have a. Is the near point 25 centimeter for this guy?
No.
More than 25, less than 25? Be careful.
More.
Haven't you seen, they hold it, usually happens when people get older, you know. Sorry, Colin. My brother has the same thing, and he had it like when he was 13. I would always make fun of him, saying, hey, you're already old, you know, because usually it happens when you're old, but younger people do have it. So that's when you have to hold it. So that means the near point, instead of being 25, became something more than 25. All right, so even before I go further, when you wear those convex lenses, tell me about the object distance and the image distance. So let's say the person can see, the near point is 1 meter. Instead of 25 centimeters, it became 1 meter. So if the person holds it at 1 meter, the person can see it, right? But no, he needs to see anything at 25, like normal people. So you have the lens on. What should the lens do?
Push it out.
When, correct. So the object distance is now 25, and the image distance should be 1 meter. Because if the convex lens that he's wearing can produce the image at 1 meter, his eye lens will take it on from there. Because even without this, he can see anything up to anything beyond 1 meter. Are you with me? Did you get it? I hope so. So DO should be 25 and DI should be X. X could be 1 meter or 2 meter, 10 meter, whatever. So that's how correction is done. So the near point is not at 25 centimeter, but say X meters. So the lens, I should have said convex lens. You can write convex lens must produce image at X meters of an object at 25 centimeter. You already got a few points if you understood this. There's certainly one question on exam 4 on correction, either nearsightedness or farsightedness. To work backwards, if the power of the lens is 5D, find his near point. So fast. Where is the near point? Find the near point. If somebody has to wear 5D, where is the near point? So if the power is 5 diopter plus 5D, where is the near point is the question. First thing you do, power is 1 by F, which means F is 1 by P, which is 1 by 5, it's 2 by 10, 0.2. Remember, it's going to be in meters, right? So you got it in meters. Next thing is you have to tell me what is DO, what is DI, what are we looking for? We got F, we got 0.2 meter. Positive 0.2 meter, correct? Yeah, so that's clear. We got that. Now you got to tell me about DO and DI. That's what we talked about. Remember, when the person holds the book at what? 25. So DO is surely 0.25 meter because we want everything in meters now. 25 centimeter. And you're looking for DI. So what is DI? 1 by F, so 1 by DO plus 1 by DI. So put that, find 1 by DI as 1 by F minus 1 by DO, which is 1 by 0.2 minus 1 by 0.25, and 1 by 0.2 is 5, isn't it? And this is 4, so which is 1, which means, in this case it doesn't matter, but remember it's 1 by DI which we are getting, you see. Some students forget that. In this case, because it's 1, it's going to be 1, but I've seen that happen like more than 75% of the time students forget that it's 1 by DI, and they will. Okay, so what's DI? In this case, it's, so is that approximately correct, Colin?